Okay, we're recording now. Okay, take two. So, hi guys, we're doing an exam pre-review for your PChem 2 exam. So, first off, with our first topic is going to be a slight thing about Slater determinants. I'm not sure if it's going to be on your exam because you did like the wave function, everything, multi-electron wave functions like in your old exam. So, I was happy this year just in case. So, basically, Slater determinants help you determine the wave function of multi-electron system. And right here we have a 1s. I have an example here showing how you would make the wave function. So one electron is in the one electron, opposite spins are both in the 1s orbital. And what you would do is you would put in the possibilities of labeling either electron 1 or electron 2 in each row. So like electron 1 can be spin up or can be spin down. Well, but electron 2 can be spin up and be spin down. And the determinant of that will be your wave function. And that's basically what state determinants are. And if it was something like this, then you would include a 2s alpha 1, and you would include a 2s alpha 2 right here below, and you'll find a determinant of that. But you'll expand this out to have like a 1s, to have like the third electron to the third row. Okay, so let's go on to the next part. So variational principles helps you determine the energy of a system that's kind of like the wave function we study, like particle in a box or a hydrogen atom. So but since variational principle can also include basis functions, which are like basis sets. So like let's say it's a linear combination of basis functions, which is shown right here. And to find the energy and stuff, we would have to use a matrix. And it is shown from this proof here that if you were to find the variational principle like you usually do for a basis function, you would find this is true. And to find these values, you would have to use matrices, and which is shown right here. And by trying to minimize this, you find that you can find the energy by finding the determinant and solving for W, which is the energy of the system. And you can possibly have like multiple values for it, depending on how much basis functions you have. And we can also solve the column vector. Getting the column vector is basically finding each coefficient for each of the that's attached to each basis function. And the column vector is basically the wave function. By finding these, you know more information about the wave function and its contributions for each basis set to the wave function. And like before, it's just an example, but if let's say you're trying to find, you can find the energy by equaling this to 0, and then you would find that W would be like some energy value. And you can use these energies here to find the column vectors. All right, so that's just variational theory, just a conceptual, get a conceptual grasp on it. Next up we have is molecules and electron Hamiltonians. Now let's say we have a diatomic molecule. We can oops, oh, give me a second. Okay, so let's say you have a diatomic molecule and you want to find out the Hamiltonian for that diatomic molecule. Well, you can use this equation here, and how each equation works is like this. So for a diatomic molecule, which is like I colored it down around here. So it would be a let's say it could be the kinetic energy of both of the atoms attached to each other, and this is equal to 0 if you're talking about the electronic Hamiltonian, and that's shown down here. And this is the kinetic energy of both of the nuclei, which are this one and this one. And since there's are two nuclei here, it'll be 2 terms. All right, and so we have also the kinetic energy of electrons, depending on how many electrons are here. If we have 1 electron here, this would just be one term here. And then and we also have to deal with the attraction of electrons to the nucleus of each nucleus. So we're going to have two terms because the electrons can be attracted to each of the nuclei. And then we have electron-electron repulsion. And finally, we have the nuclei can because they're both positively charged, they can repel each other. In electron Hamiltonian, it's just basically all that, but except because we treat the nuclei as fixed, we don't have to include it in the term. And so when it asks for you for the full Hamiltonian, you would use this, but if it asks for electron Hamiltonian, you would include this without the kinetic energy of the nuclei. Now, this is just an example in lecture how they were able to basically solve for the wave function. Basically, this, by solving this, we can find out what the energy is. And so by applying it to, let's say some trial functions, these here, we found that we can solve for the energy. And HA is just basically the energy of the 1s electron. And HBB is just 1sb. And this is one that's important is SAB, which is the overlap, which is equal to 1SAB and like forwards and backwards. So basically like and this is used by a very variational theory to solve for these energies. Okay. And this is just to show by solving this, we get this wave function here. And this shows if this was positive, this would be bonding. If this is negative, this would be anti-bonding. And we'll go to the next one. So this is an example of, I gotta show you an example of how to solve this. So basically, it's telling you to solve for the normalization constant n, and it's asking what are the coefficients of a and b of the corresponding normalized wave function. So basically what you do first is find a normalization constant, and we found out normalization can be solved like this. And this is just the same as, because we're dealing with zero, negative infinity to infinity. And we can just write it like this. So let's just try to solve this. So this is equal to okay, so it's equal to that, and that's going to be minus 0.877. And that's multiplied by 0.223 1SA minus 0.877 1SB2. Oh, and we do this. So we can solve this, and this will just equal to 0.223. After multiplying, that's 1SA. There's 1SA. And that's minus 0.223 times negative 0.877 times 1SA, 1SB. And then negative, and that's minus 0.877 times 0.223 1SA, 1S, wait, minus A, and then that's going to be minus 0.877 times 1 SB, 1 SB. So because these are normalized s orbitals, this would equal 1. This is an overlap interval, which is, and they're shown here what the overlap interval is. So this is going to be equal to 0.26. That's going to be 0.26 because that's an overlap interval. And that's equal to 1 because of normalized wave function. And because we have overlap intervals, is because this has different coordinates. This is the coordinates of the electron on the other diatomic atom, and this is the one on the other diatomic atom. So atom A and atom B, and that's why we have overlap intervals. They just mean they're not they have different coordinates, and that's why the intervals actually are not equal to 1 or 0. So from that, you can solve this, and we would get, hopefully I solved this here. And let me just switch these here to make much more sense. Okay. Hmm. 0.223. Oh wait, that's going to be it squared. Forgot that. Oh wait, it's going to be plus and minus 0.8 squared and I remember here, and you got this other side, and so -2. So to solve for this, we just put this in -2 power, -1/2 power, I mean. And you would find that n is equal to 1.105. And to find out what A is equal to, you just have to multiply. So A is equal to 0.223 times the normalization constant, because after having a multiplication constant, and this is just going to be it normalized, it's going to be n. is going to be, so the reason why we multiply it is this, because this is equal to n over n1. And so multiplying a normalization constant, we get this is equal to times 0.223, 0.246, and b is equal to 0.223 times n, which is not 223, negative 0.877 times n, which is equal to negative 0.969. All right, that solves that question. Okay, so for this question, I'm just gonna do part B. It has to do with normalization and stuff. So it's asking us to find the normalization constant for the wave function psi b 1, 2. So to do that, I mean, oh, that's A, the part A, yeah. We would just have to do usually, so this is just and I'm just gonna like skip some stuff a bit. So this is just 1s1 3s2 minus 1s2 3s 3s1 multiplied by beta 1 beta 2 beta 1 times beta 2 and it's basically the same thing, but it has the opposite. It has the ket. It has beta 2. I'm just gonna skip a few from just so multiplying 1s with this is a normalized wave function. This is 1. And we're gonna multiply this by this, and that's gonna be 1, 2. And it's gonna be minus 1s1 with that is going to be 0 because it's a 1s1 ket bra with this. Must be there. This with this, and they both have different eigenvalues, meaning they're orthogonal, which means the integral will be 0. So we have a 0 here. And the outside, this would be beta 1 with beta 1, beta 2 with beta 2, and now equal 1. And this is going to be with the normalization constant. I put it to the other side. This will be n to the negative 2. And n will equal 1 over radical 2. Okay. Give me 1 second. Got it. Okay. Okay, it's talking about homonuclear diatomics. So basically, it has to do with making a bond, a molecular orbital diagram, and we're talking about how where did it come from solving from understanding these concepts. So as I said before, HAA and HBB are different. There's the energy of atom one, is the energy of atom B. So these are two different atoms, homonuclear diatomics, meaning that they're two different atoms together. And by solving the determinant like we did for variational theory for diatomic, we can find out the energy of this, and this will be the WA will be the energy of a antibonding, while WB would be energy of a bonding. And this is shown in the diagram below. And this symbol here, which is kind of like I forgot what it's called, but it's right here. It's just related to the absolute value of ml, and we use these on each atom. We add these together to find out the molecular symbol for it. So I'll show you here next. So this is going to be the total orbital angular momentum, and we add the mLs together to find out what the symbol is. So if it's equal to 0, this is equal to this, and if it's equal to 1, it's equal to this pi thing, and if it's equal to 2, it equals this triangle, this theta symbol. The bond order can be calculated by finding the number of electrons in the antibonding and number of electrons in the bonding. By subtracting this and dividing by 2, we can find out the bond order. And this here is just an example of a molecular orbital diagram and how we would figure out what the information that I just talked about. And I'm not going to go into depth with this example, but it's going to have the symbol here. And you guys can work out this example yourselves here, and you'll lead to the same answer. Did I do that again? Oh, backwards. Okay. So it is asking us to figure out the complete Hamiltonian of a diatom of helium hydride. Just kind of go notes here. So to figure this out, the complete Hamiltonian includes the only difference between the electron Hamiltonian is that it includes the kinetic energy of the nucleus. So if we solve this here, we can solve for this by just splitting the terms. So I'm just going to draw helium oxide right here. So first off, we're going to deal with the kinetic energy of the nucleus of both nuclei on a diatomic atom. So because there's two atoms on a diatomic atom, of course, we're going to have two terms. So I'm just going to do this. This is equal to negative h bar squared. 2 is going to be the mass of the nuclei. So it's going to be the mass. We're going to have 2 termites of the hydrogen. And then we're going to have, and the other term is going to be minus, and let's just call this, oh, give me 1 second. Let's go back. And then we're going to have another term, minus h bar squared over 2m helium, which is going to be this. And those are the two terms, the kinetic energy of both nuclei. So next we're going to have the kinetic energy of the electrons. So since helium has 2 electrons and hydrogen has 1, they're going to combine and make the molecular orbital, which is going to be 3. So we're going to have 3 terms. So I'm just going to put, because we can distribute out h bar over 2 me, we can literally just put this, and it's going to be electron 1 plus electron 2, and that's plus electron 3, because we can distribute out this term here. And we're going to deal with the attraction to the electrons to the nuclei. Since we have 2 nuclei and 3 electrons, we're going to have 6 terms altogether because each electron can attract to each nuclei. So we're going to have, let's see, okay, so it's the charge, let's say hydrogen. Then we're going to have -1 e squared. And I'm going to distribute this out. Actually, I'm not going to distribute this out. So it's going to be much more simple to understand. So then we're going to have r of the distance h, and then we're going to have electron 1 minus 1 e squared, and that's going to be electron 2 minus 1 e squared electron 3. And we're going to have the other 3 terms, which are going to be -2, because that's going to be the charge of the helium atom, and it's going to be RHE1 minus 2E, RHE2 minus 2E, okay, RHE3. All right, we're almost done with this. Next thing we're going to have is electron-electron repulsion. So then we're going to have electron can interact with each other 3 times, I believe. So you just do this, so you run it a combination. So you're going to have R12, then we're going to have E squared, R23, and the final combination is E squared, R31. So you can't have R13 combined or R32. You can only have the first possible interaction they each electron can have in each other. And it'll be this combination here. And then we're going to finally have the repulsion between, we're going to have the repulsion between each other from each of the nuclei. And a nuclei would be, so 1 times 2 times E squared, and that's going to be the distance between H and HE. All right, and we can, I do not want to like, when you write this, I would suggest do each term at a time and then write the full Hamiltonian after, which is right here. And then for the part, then for the second part, it's asking for the electron Hamiltonian, which is the same thing, but just not this term here. So we're just going to write for electron Hamiltonian, this is equal to, put part B here, this electron Hamiltonian, and this is equal to kinetic energy electron plus V E, and then plus V and M. All right, and that'll be your answer. Because you established the terms before, you can just write this down there, and you don't have to write down the whole thing if you defined it. Sketch the orbital diagram. Okay, so asking you to sketch the orbital diagram. This, and it's asking for the electron configuration. So if you guys took inorganics, will be easy for you guys, but just a reminder. So it matters what we put the 1s orbital, the atomic orbitals. Because helium has 2 electrons, it's stable because of its 2 electrons in its shell, and it's a noble gas. So it's going to be a lower energy, and H is going to be here because it has 1 electron and it's less stable than helium. And these will interact to make 2 molecular orbitals, 1 bonding and 1 anti-bonding. This will be 1 sigma, and this will be 1 sigma star. Since helium and hydrogen both have 3 electrons between each other, you're going to put 1, 2, and then 3. And that'll be your answer for this. It's asking you for the electron configuration. Oh wait, this is going to be Grada and Ungrada. And it's going to be just literally this. It's going to be 2, and it's 1 sigma Ungrada star, and it's going to be 1. And that'll be your electron configuration. All right. it is asking you for the bond order between all these. So let's start with the bond order between regular helium hydride. And that's going to be 2 electrons in the bonding and 1 electron in the antibonding. So it's going to be 2 minus 1 over 2. And that's going to be equal to 1/2. If we're talking about, let's see, I want to put this first, but yeah, it's going to be positive. You put the positive here. Yeah, you put positive. So it's going to be the same thing up here, but it's going to have 1 less electron, which means it's not going to have any electrons in its antibonding orbital, which means it'll be 2 minus 0 over 2, which would be 1. And its bonding orbital. So that would be 2 electrons now because 1 extra electron in its bonding orbital. So it's going to be 2 minus 2 over 2, which will be 0. And part D is asking what is the bond order in each of the following helium of each. I mean, it's asking which one is most stable, and it's going to be this one's the most stable because it has less electrons in its it has no stable because it has less electrons in its anti-bonding orbital. Okay, and this here's one problem in recitation. Now, it's asking you the calculated molecular orbitals of H and basically helium hydride ion are given by this expression. Justify the relative size of the coefficients. So because of, this is supposed to be one sigma star. So because of the closest of energy between here, so because the hydrogen atomic orbital is closer to the anti-bonding orbital, it's going to have much more of a contribution, which means its coefficient is going to be higher, and that's going to be shown here. Oh wait, that's not here. Oh, right here. And because because helium is not close to energy to the anti-bonding, it's going to have less energy. It's going to have a lower coefficient. And it's the same. It's the reverse for the bonding, which means that this is closer in energy to the helium atom, and that means the coefficient is going to be much higher than the hydrogen atom. So the coefficient is going to be less. And we can just put, because hydrogen is closer in energy to the anti-bonding orbital, it will contribute more to the molecular orbital, well, than helium. And it's going to be vice versa for helium. Okay. Right here. So next topic is Huckel method, which pretty much just talks about the conjugation of electrons. The conjugation of electrons between each other in a hydrocarbon. So by solving the determinant here, we could find out the energies of the hydrocarbon. And this is going to be based on the following rules. So SUV equal to 0 if these are not neighbors, and it's equal to beta if they're neighbors. So I mean, Give me 1 second. Let me repeat myself. So if SUV, okay. Did I forget to write down a note? So this is equal to 0 if they're not neighbors. One more. I forget. If U is equal to V, but neighbors. Oh yeah. Okay. Yeah. So I am right. So okay. So SUV, if they're not neighbors, the SUV is going to equal to 0, and beta is going to equal to beta if U equals V, and E equals 0 otherwise, not neighbors. Wait, why? Oof. Okay. SUV, and then okay. S11, SK. Okay, I figured out why I did wrong. Mhm. Can you cut this out? Because I just got stumped just now. Okay, so HAK. Okay, I got it now. All right, so we start from the beginning. If SUV is equal to 0 if they're if we're talking about the same atom. So let's say if S and U don't equal to each other, then that means SUV is equal to 0. If S and U and V are equal to each other, meaning we're talking about the same atom, then they're not neighbor, then they're equal to 1. And it's 0 otherwise, which I just said, which made me confused. Okay. So if you want to talk about let's say if we just wanted the determinant itself and you don't have to worry about H or S, you can say if U equals V, this will be this term. U doesn't equal V, it will be this term. And this does, if they're neighbors too, they're equal beta. And then finally, if they're not neighbors, equal to 0. And if you want to put it in terms of X, you can solve for the energy, you can use this here. So if they're on the same atom, X. If they're not on the same atom, but a neighbor is 1. If they're not on the same atom, they're not neighbors, it's equal to 0. And how I'm talking about this is a little confusing, but it makes much more sense in the example right here. So let's say we have ethylene. We found if we're talking about S11, so we're looking at atom 1 to atom 1, then this will equal to 1, and this would be the same for S22. If we're talking about S12, because these are neighbors, these are not, I mean, because these are, it's not the same atom, U and V are not equal to each other, S12 and S21 will equal to 0. But H11 and H22 equal to alpha, and H12 and H21 will equal to beta because they're neighbors. And beta is a negative constant, and this will help out with determining energy later on. So from here, this is going to be relating back to here, HUV minus E over SUV, and H11 is equal to alpha, and then that's minus 1 times E, which is right here, and it's going to be beta, and it's going to be beta time, the beta in here is going to be alpha minus E, because it'll be H22 minus HS22, which is 1 times E. And we're gonna have to solve for determinant and then solve for 0. So then we put everything in, like I said before, using this. So this will be X, this term will be X, this will be 1, and this will be 1. And from solving this determinant, we found out that the energy, that X is equal to this, and to solve for energy, we know that this is going to be equal to X. So then we can solve for an energy here, and the energy, this will be the two energies. Okay, so based on that, we can find out the what the energy and the energy levels that they're at. So because beta is a negative constant, whatever times by beta will make it much more or less of an energy. So plus beta would be down here because it's plus by a negative quantity, and minus beta because minus negative times negative is positive. This will be adding to the energy. So it'll be up here. And the lowest occupied, and we're gonna find out the lowest occupied on the highest occupied orbital, which is basically how it is because this is the highest occupied orbital. And there's no electrons here, which means it'll be the highest occupied, lowest occupied orbital. And from here, we can also from this solve for the energies based on the coefficients. So like I said before in variational theory, you can solve for the coefficients with the energy, and then from the energy, but in this case, we can use the coefficients to find the energy of electron in an orbital, like the total energy of that system by basically, let's say for this, it'll be 2 electrons times that energy here, and that'll be your total energy of that molecule. And we can find out the pi charge of the carbon and the carbon M, and also the pi bond of bond Mu. So like between maybe this one here, 1 and 2. Okay. So this here, perform a Huckel calculation for the Ali radical CH2CH2. So this will help me. Okay, so we can solve for the energy by using this determinant. And this is equal to alpha minus E, because this is going to be 1 atom to 1, and then it's going to be alpha minus E. And because this is a neighbor, this will be beta, then 0. Then this is beta, alpha minus E, and this is neighbor 2, it's going to be beta, and it's going to be 0 because this is not interacting with electron 1. This is going to be beta, this is going to be alpha minus E. And then we find a determinant and then solve for 0. So we put it in terms of X. This will equal to X, then 1, then 0, then 1, then X, then 1, then 0, then 1, then X. So from solving this determinant, I have another page. So to solve this determinant, we basically do this. So we look at the first row and look at the first column, and then we crisscross multiply, and then this would be X, which would be the first row of the first column, and then below here would be X times X minus X squared, That's to be minus 1. This is 1 times 1. And the next would be 1. And this would be this multiplied by x. So it's going to be this multiplied by x. And 1 multiplied by 0. So this would be just x. So it'd be minus 1 times x is going to equal to 0. And then we can simplify x out. This will be x squared minus 1 equal to 0. Then that will be x squared minus 2, and that will be equal to 0. That means x is equal to 0. And then from solving this, I'll just skip ahead, but this will just be x is equal to plus or minus radical 2. And like we said before, E is equal to alpha minus x of E. So we have 3 energies. So right here, if we put this here, let's say radical 2, negative radical 2 would be alpha minus radical 2, and that would be greater. So this would be alpha minus radical 2 beta, because the negative quantities will just add to alpha. And then below we'll have alpha plus radical 2 times beta, because this would subtract from alpha. And this will just be alpha, because 0 doesn't contribute at all. Okay, from here, I think that was pretty much it. It's asking what the electron configuration is. So since there's 3 electrons conjugating in the system, this will just be 3 electrons. So it'll be 1, 2, 3. Okay, so that will be it. And it says calculate the pi bond orbital between carbon 3 and carbon 4. So how this thing works, it's first I would suggest you draw on the molecular orbitals. So since there's 3 wave functions here, you're gonna have 3 energies. So I'll just draw energies 1, 2, 3, and this would be alpha 1, alpha 2, and alpha 3. And then it's asking us to this is hexatriene. So it's going to have a bunch of double bonds. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that's going to be 6. So you're going to be 6 electrons conjugating in the system. So 1, 2, 3, 4, 5, 6. And we're going to use this information to solve for our equation below. And that equation is going to be pi bond order is going to be equal to P the I to occupied and I times the coefficient. So this equation is a little weird first looking at it, but how it works is this is so pi order just means the pi order between 2 electrons. So this is the other 1 electron, this is the other electron. And this is going to be our molecular orbital. And this is going to be the number of electrons in that molecular orbital. So from here, let's start off with the first one. So the first one has 2 electrons in the molecular orbital. So we're going to have we're going to have a term that has 2 here, and it's going to be the coefficient of that electron 3. So electron 3 is right here. The coefficient of electron 3, and that's going to be 0.5211. And it's going to be a coefficient of electron, the coefficient on electron 4, and then that's going to be 0.5211, which is over here. And then we do the same thing we do 2 times, and it's going to be coefficient electron 2. And because we have 2 electrons, because we're in the second orbital this time, and then we have another coefficient, it's going to be 0.2319 times 0.2319. It's going to be a negative, actually. And then we do the same thing here. And it's going to be plus 2 times negative 0.4179 times negative 0.4179. And that's going to equal to 0.7848. And just know that you're going from here to the occupied orbital. So you're going to, let's say if we have 4 electrons and no electrons here, you would only go up to the second orbital because there's no electrons occupying that. And even if we were to expand it that much, we have 0 electrons here, which means the term wouldn't matter. Okay, so I'm not going to do part B because it's pretty much the same thing. But let's go to, all right, the last topic, diatomic, gravitational, and vibrational. So basically, he teaches you about the selection rule, which basically says that if you increase in rotational energy, you can only increase it by 1 energy level by J, or by below energy level, -1. So the change in that would be 1. And he teaches you about also the spacing between each energy level is found by this equation here. And I would suggest to memorize this equation because it'll be used for, let's say, if you're recording the band, the wavelength of an energy level jump, you would use this equation to find what B is equal to or what J is equal to if you're given either one or the other. Okay, so I don't know if you're gonna ask you this in the exam, but this is just a good one to know. The population of finding a molecule, probability of finding a molecule in the absolute energy level. So it just helps you with solving for that specific energy. And also, if you take the derivative of this and find the maximum equal to 0, you find this, and this will be the J level where you'll find the most molecules. And this increases with temperature because if you really think about it, if temperature is increasing, you have much more energy, meaning that the J level will be higher because higher J leads to higher energy. Okay. And this is the correction to, because it's in spectroscopy, they found that there's actually a correction due to rotation that distorts the bond a little bit and the bond length. So that means that this term accounts for that. And if you find a difference between the 2 energy levels, so like I did right here, you'll find that this is equal to this equation. And now vibrational spectra. You guys basically electrons, molecules vibrate at a certain frequency with specific V. So if you were to put this in terms of energy, you can use this equation here. And then if you're finding let's say the difference between each energy level, you can use this equation here. And finally, you can use the selection rule where if it's the same thing as J, it can only increase or decrease by 1 energy level. Okay, so enharmonic correction actually is the same thing as the pretty much the correction to the rotation. The correction deals with, okay, it's not going to be totally perfect. We're going to have this term here that corrects for the energy. And Because of the correction, it turns out that this is possible to increase by maybe 2 energy levels or 3. And that's called the first order and second order, the first and second overtones. As shown right here, the fundamental will just be what we know and what we want in nature, which is for it to jump one energy level, but turns out it jumps more than one. Okay, and it's shown from here, just between each energy level, it's equal to this and equal to this. All right, and the difference between each energy level, I mean, actually is this. It's approximately equal to this, but basically, with these terms here, if you were to say the difference between, let's say the fundamental, so I just jumped to energy level, the difference in energy of that will equal to this equation. And let's say we jump into the second energy level and not even go to the first. So that means the difference between the energy levels would be this. And then I jump to the third energy level from 0, and this would be this equation. All right, and the rest is just useful equations to know. I wouldn't worry about this. Okay, so let's start off with this equation here. Okay, so let's say we're trying to figure out what it says that the J2 to 3 pre-rotation from the ground state of K potassium chloride occurs at here. Neglecting centrifugal distortion, predict the frequency of the J3 to 4 per rotation. So it's asking us to figure out what the next jump would be, and we can use our equation that we found here. So distance between each energy level would be J to J plus 1. This would equal to 2B J plus 1. Now to figure it, now we're given what this is equal to from this, and we're going to use this to solve for B. Now, just remember that you have to use the previous J level that was jumped, so 2. So then we will plug in 2, 2, 4, 1, okay, megahertz. And then that's equal to 2B times 3 plus 1. And B is equal to 2, 3, 5 hertz. Okay, so then from here, we can plug in to our equation from 3 to 4, and we would get 2 times 3, 7, 3, 7 hertz. And then that's the previous energy level, which would be, oh, sorry, this is a 2 here. This is the previous energy level, which is 3 plus 1. And you will find this is equal to 29880 hertz. Okay, so from here, you would solve part A, and it's now asking you to calculate the same thing, but this time it has an isotope, and this isotope has chloride equal to have 35 AMU. So to solve this, we would pretty much do the same thing like we did in the last review. If you remember, we have to put it in terms that we previously found so we can solve for it. So in this case, we have a new rotational constant because a new reduced mass due to this isotope. This is equal to h bar squared over 2I. And the only thing that's different is the moment of inertia. So we expand out the moment of inertia to 2m. And since the bond length in the chain, the only thing different is m, the reduced mass. And so we solve for what reduced mass is equal to. And we put this in terms we understand. So we're trying to get m times like some constant w, and it's going to be equal to m times. And we do this so that way, okay, m times r times w, and then we're going to get this equal to b over w. And from solving this, we know what B is, and we solve for W, we can find out what the rotational constant is and just solve for the equation. So basically, we solve for the new, we basically solve for W, and W is equal to, and this is, so the reduced mass equation goes like this. So it's basically the mass times the mass of the other diatom molecules multiplied together, so the masses of both. So for this new one, it's 35 AMU times 39 AMU over the addition of both the reduced mass of 35 AMU plus 39 AMU. And it's going to be over the reduced mass of the old molecule, which is 37 AMU times 39 AMU. And this is over, 37 AMU plus 39 AMU. And this is going to equal to 0.9715. So from here, from solving this, we would get that W is equal to that. So we can expand out the term so we can figure out what the new rotational constant is, which is B over 0.915. Now I'm going to keep it like this so that way we can solve, because this is actually easy. It's going to be easy now with just me just leaving it like this. So because we so let's solve for V, the new V of 3 to 4, which is equal to J plus 1 times B, and then that's equal to oh, 2B. Sorry, my bad. 2B. And that's going to be equal to 2B 2B 3 plus 1 divided by W. And we already know what this term is because we solved it up here. So then this is going to be equal to 2, 9, 8, 0 hertz over 0.9715. And that's going to be equal to oh, give me a second. 29880 by 0.9715. 30756. Okay, and that solves that question. Now for problem 3, we're going to have to solve for the first order and second order of xy. So basically, they want us to solve for these constants using the following information. Okay, so the band origins of the first and second orbitals of the diatomic molecule xy are this, and and the second overtone is this. And want to sell the constant based on that. Okay, so we know we can use the following equations to figure out what that is. So it's asking us for the first harmonic correction, so we don't have to worry about these here. And so we're going to have these two terms here. And then 2WE minus 6WE XE. So to solve for this, all we would have to do is just multiply by, we just have to like multiply the whole equation to cancel out one term. And this is just linear equations. Basically what we learned from back in algebra. So basically just multiply this to cancel out, let's cancel out 2 here. So let's just multiply this by 3, by -3 actually. And this would make this cross out with this. And then this would be negative WE, because negative WE, -3WE plus positive 2WE would be -3, -1WE. And this is just going to be -3 WE, -3, 0 to 1, plus V 0 to 2. And you told us that those quantities already. First is 7, 5, 2, 1, 0, 1, 2. 10.58. My calculator. It'll be 11,605.546 equals WE. So we have the first and the constant XE. And we want to find out XE. So then we can just solve for this. Okay, 7. We'll just plug into the first equation here. and then XE is equal to this. Five, actually makes it 6, 0. Okay. And let me just double check if I got this right. This was a long problem to do. Into the calculation error. That's great. What is wrong? Yeah, I used that equation. Just fix that real quick. So I used the wrong equation, but it's pretty much the same principle. So this time you multiply by -2. Just will cross this out. And then all we're left with is -2, -2, 3, 0 to 2, plus the 0 to 3. And then that's negative 4WE plus 3WE. And then a negative that. And I'll just skip ahead a bit to solving this. And that will equal to 4084. Here's a -1. It's gonna be 0.44, but it's whatever. And then we can pretty much just plug this in. And I'll say the first equation. And I'll just do this because I forgot to. Okay. And then 2 times whatever we solve for WE, which is 4084.44 minus 3WE XE. And then we get, oh yeah, let me plug in what this is. With the first overtone being 7521.0. And then from here, we would find out that WE XE would equal to equal to this. And then from here, we can just solve for what XE is equal to. and we can just plug in what this is into here, and then we would find out that XC is equal to 2.64 times 10 to the negative 2. And for the next part, I'm not going to like go into depth, but all you pretty much do is just use the first equation, which is this one here. And you would just plug in your constants to find the fundamental, basically the fundamental transition. So that's pretty much all I have for you guys. If you have any questions, just text in the group chat or just email me or whatever. And that's it.